Today I'm going to talk about our research on the design and implementation of ipShield, which is a framework for enforcing context-aware privacy for sensor data on mobile platforms. So cell phones today are no longer mere communication devices. They are packed with a lot of processing power, and they are also equipped with a wide variety of sensors. So this enables the cell phones to not only gather but also process a large amount of personal sensor data. And what this has also enabled is a sprawling ecosystem of applications which thrive on the continuous and unobtrusive collection of these sensor data. Now, using this data, the applications can draw inferences, and some of these inferences are utility providing as far as the user is concerned. That is, this is the reason why the user goes ahead and installs these applications on his phone. But at the same time, the data can be used for drawing inferences which are sensitive or privacy violating for the user. So let's take a specific example here. The user installs a health application on his phone. Now, this application has access to the accelerometer and the gyroscope sensors. Now, using the data, the application can create an activity profile of the user over a period of time and use that to provide a fitness score, which is utility providing to the user. But it has been shown that when we use the soft keyboard on the phone, the keystrokes that you make, they create a very unique signature pattern in this sensor data. And this pattern can be exploited by this application to actually perform key logging and actually use it to infer sensitive information such as password and PIN. So the idea here is that you share data with applications, and the same data can be used for deriving inferences which are utility providing, as well as inferences which are sensitive. And what we do is we club all the utility providing inferences in what we call a whitelist, and all the sensitive inferences into what we call as a blacklist. Now, the goal of our research is to design and build this inference firewall, very similar to a network firewall, which will be able to intercept sensor data and transform it in such a way that the utility providing inferences could actually be made with high accuracy, and the sensitive or blacklisted inferences could actually be blocked. Now, there are prior notions of privacy which have been explored, particularly in the database community. And the setting typically that they follow is one in which there are multiple users who generate and store their data in a population scale database. Now, if you look at the data that is being shared, it has a wide variety of attributes, but it can generally be classified into three broad types. The first one are the personal identifiers, for example, the name, social security, or any other identifier which uniquely identifies the individual. Then you have the quasi-identifiers, for example, age, gender, zip code. So these attributes do not uniquely identify the individual, but then when you correlate them with auxiliary sources of information, you can narrow down the search space. And finally, you have the actual sensor values which are stored in the database. Now, there are metrics such as K anonymity, L diversity, T closeness. So these are the different, these are basically guiding metrics which tell you the extent to which the data needs to be obfuscated. So the idea here is that when you share data, you strip all the personal identifiers and you obfuscate the quasi-identifiers in such a way that the identity of any single individual in the release data set is indistinguishable from K other individuals in the same database. So basically, you are trying to achieve privacy in numbers. Now, the other predominant notion that we have is one of differential privacy. And the idea here is that you execute aggregate queries on a population scale database. And you take these query responses and add structured noise to it, typically from a Laplace distribution. And you release this obfuscated query response to the adversary. Now, on observing this, the adversary should not be able to figure out the presence or absence of a particular individual in the database. But the setting that we consider in our problem is very different. Here, there is a single individual who is sharing data with an application or an app provider. So the identity of the individual is typically known. So instead of the traditional notions of privacy of data or secrecy or privacy of identity or anonymity, we have a different flavor of a privacy problem, which we call the privacy of behavior. So in this case, the identity of the individual is known. So what we are trying to protect from the shared data is a subset of inferences or certain behaviors which are private to the individual. So if you look at the controls that are provided by current systems, they are often insufficient when it comes to protecting behavioral privacy. For example, Android currently lists the set of resources that are accessed by an application. And at this point, the user has the option to either grant access to all these resources or not install the application at all. So this is a binary choice that's available to the user at install time. If you look at pDroid, this is a variant of Android. What it allows the user to do is configure fine-grained access control policies on these resources. Here again, the user has a choice to configure these rules not only at install time, but also at runtime. But the problem is that these policies are static in nature. And then you have systems such as Protect My Privacy. So this is built on top of iOS. It does not handle sensor data, but what it allows the user to do is configure and share random data in place of sensitive information. For example, here, Facebook requests the user for a context list, but the user can configure Protect My Privacy to share a randomized context list in place of the actual context list. So what we have here is a very small representative set of privacy-providing systems. And there are a lot more systems out there. But the basic design philosophy behind the systems is that the user needs to configure these fine-grained access control policies for these resources or sensors. But what we are advocating as part of our system is that the user should only be required to configure these privacy policies at a very higher level abstraction of inferences that could be derived from the sensor data. And it should be the onus or the responsibility of the system to take these higher level preferences and drill them down to lower level rules which can then be enforced on the sensors. So with that goal in mind, let's look at the design requirements for ipShield, which is our inference firewall. So if you look at current operating systems such as Android and iOS, what they do is they group all the sensors that are available on these smartphones into two basic classes. The first class consists of sensors such as your GPS, camera, your microphone. So these are supposed to be privacy-prone sensors. So the access to these sensors are mediated through protected APIs. But then you have this other class of sensors, which comprises sensors such as accelerometer, your gyroscope, light sensor. So these are supposed to be benign or innocuous sensors. And these applications have unrestricted access to these sensors. But what we have recently shown is that if you take enough data from these harmless sensors, you can still use sophisticated machine learning techniques to learn a lot more about the user and mount sophisticated privacy attacks. So what we wanted to do as part of ipShield is ensure that every resource or every sensor that is being accessed by an application is monitored, and this information should be presented to the user. Now, as I mentioned before, these systems typically present the user with a list of sensors or resources that are accessed by an application, and often a user does not really know the implication of granting access to a sensor or blocking access to a sensor. Like if I ask what will happen if I grant access to an accelerometer, I really don't know. So what we wanted to do is we wanted to provide the user with a better privacy abstraction that is present the privacy risks in terms of more meaningful privacy abstraction of inferences that could be made from these sensor data. And now if you consider the data flow in ipShield, the user provides their privacy preferences in terms of a whitelist and a blacklist of inferences. So what we wanted was this translation block which could take in these higher level preferences and drill them down to lower level policies. So we needed a rule recommender in place. And we also wanted a mechanism by which the user could actually override these auto-generated rules and can configure their own fine-grained policies. So we allow manual override. And finally, we took all these rules and created a system which could enforce these rules in a safe and secure way so that a malicious application or a malicious user cannot tamper with these rules. So in the next few slides, I'm going to talk about how the rule recommender works in ipShield because it forms the core of our work, and look at the design choices that we made for implementing this rule recommender. Now, if you think about the rule recommender, the grand goal here is to generate a plan which will containing the context-aware obfuscation of sensor data. So it should tell you how should you transform your data before sharing. And it should be depending on the prioritized whitelist and a blacklist that has been configured by the user, such that the accuracy of the whitelist is maximized and the accuracy of the blacklist is minimized. Now, what we found is it's very hard to come up with all-purpose or general-purpose rule recommender, and we are working on it. So we have some bounds. We did in our concurrent work, we look at information theoretic formulations of this problem, and we have certain bounds, but it's hard to translate those bounds into practical system. But we are still working on it. So what we did in this work was to adopt a strategy of divide and conquer and split the problem into two parts. In the first part, we wanted to generate a rule recommender, which will recommend a plan containing allow deny rules on sensors. So instead of generating how to obfuscate sensor data, we are generating a binary policy of which sensors to allow and which sensors to block, again depending on the prioritized whitelist and the blacklist configured by the user, such that the accuracy of the whitelist is maximized and the accuracy of the blacklist is minimized. And in the second part of the problem, what we wanted to do was allow the user to override or augment some of these rules, some of these generated rules, and create their own fine-grained policies. Now, we introduced two new elements in this problem definition. The first one was accuracy of the inferences. Now, to create a search space over which we could run our optimization problem, we created this inference database. So what this table stores is the maximum accuracy with which a particular sensor combination can be used to derive a particular inference. So for a sensor combination type and a given inference, this table stores the maximum accuracy with which any machine learning algorithm is able to make that classification. So we derived this table out of our own exhaustive experimentation and also by extensive study of around 100-odd papers which report results on the accuracy of their machine learning classifiers. The second element of our problem was this priority. So we allow the user to not only configure a whitelist and a blacklist, but also associate a priority value to these inferences. So in ipShield, the priority numbers are from 1 to 10, where a higher value indicates higher priority. Now, these notions of the notion of priority has different connotations when it comes to whitelisted inferences and blacklisted inference. For a whitelisted inference, a higher priority indicates that the user really wants this inference to get through, or in other words, is willing to tolerate less utility loss when it comes to this particular inference. And in terms of blacklisted inference, a higher priority indicates a higher desire to block that inference. And we allow the user to set the priority to the highest value, and when he does that, it's an indication to the system that the user wants this inference to be blocked and nothing else. So based on these notions, we have the following optimization. We formulate the following optimization problem for our rule recommender, wherein overall sensor combinations, we maximize the accuracy of the prioritized whitelist, minimize the accuracy of the prioritized blacklist, and we ensure that whenever a user indicates that a particular inference is blacklisted with highest priority, that particular inference is blocked. Now, this problem is NP hard, and we don't have a poly-time solution for this, but it could be solved because the number of sensors that are used by applications is really low. So to see how the rule recommender works in practice, we have this inference database. So the user can select a whitelist and a blacklist. So in this case, activity is the whitelist, and location and on-screen taps belong to the blacklist. The user can also specify a priority, in this case 10, 4, and 10. So by specifying a priority of 10 for the on-screen taps, which is a blacklisted inference, the user indicates that it needs to block this particular inference. So the search space now reduces to only those rows in the table for which the accuracy of detecting the on-screen taps is equal to 0. And over this reduced search space, the optimizer then maximizes the accuracy of the whitelist, and it turns out that GPS plus Wi-Fi are the sensors that should be turned on for this particular whitelist and blacklist combination to get through. So this is how our rule recommender works in practice. Now, we also implemented ipShield on Android. Now, one of the key requirements to implement ipShield was that we had to intercept the sensor data and transform it before sharing it with the app. So it became imperative that we understood how the sensor subsystem works in Android. So out here, we have a very simplified representation of the sensor subsystem, and the blocks which I have marked here are part of the data pathway from the sensor to the application. So you have the system services, which in this case which is sensor service and location manager service. So these services continuously poll the hardware sensor for data. This data is then sent to the sensor manager and the location manager. These managers are application-facing proxies of these system services. That is, the system services are not directly accessible to the application that you write on your Android phone. And then these applications can create objects of these location managers or sensor manager and access sensor data. Now, if you look at this data pathway, there are multiple points at which we could have intercepted the data and perform our privacy translations. But we found that the application and the manager are part of the same process. What it means is that the application also has access to the address space of the manager. So in theory, during runtime, the application can go ahead and modify the address space and modify the changes that we have made, thereby neutralizing all our efforts. So we made our changes within the system services layer. These services run in a separate process, which is system-owned, and hence are protected by the process-level isolations, which are enforced by the underlying Linux kernel. Now, looking at the implementation of ipShield, we made changes to various layers of the Android OS to implement ipShield. As I mentioned, for any application to access sensor data, it has to go through one of these two services, that is sensor service or location manager service. So both these services have an idea as to what all sensors are being accessed by this application. So we tapped into this information and provided it all the way to ipShield. Now, I should note here that, ipShield operates in two distinct modes. One is the semantic firewall configurator mode. In this mode, the user observes the different inferences which could be made by a particular application and configure the whitelist and the blacklist respectively. For privacy abstraction, we implemented the Inference Database, which takes these different sensors which are being accessed by an application and provides a list of possible inferences that could be made using those sensors. We implemented the rule recommender, the algorithm that I just mentioned. And finally, we have this other mode, which is the direct configurator mode. In this mode, the user can manually configure policies. We also implement a context engine. So this engine takes into account raw sensor data and provides the current context state of the user. For example, it tells the user whether he's running, he's walking, and then the user can use these as to create context-aware rules. Finally, for enforcement, we have the obfuscator block. We implemented this obfuscator block within the system service. This block intercepts the sensor data, applies the rule on the data before releasing it to the applications. And this is how the user interaction with ipShield looks like. So whenever the user clicks on ipShield, he's presented with a list of applications that are currently running on the phone. And for each application, he can see the set of inferences together with the set of sensors which are being accessed by the application. In the semantic configurator mode, the user is presented with a list of possible inferences that could be made. So at this point, the user can select a priority to an inference, and he can also classify the inference as allowed or blocked. That is a whitelisted inference or a blacklisted inference. The rule recommender at this point tells the user what all sensors to be suppressed or allowed. And the user can also go to the direct configurator mode. In this mode, he's provided with a list of privacy actions that he can configure for each of these sensors. And each of these rules also support a wide variety of context that could be added along with it. So we evaluated the feasibility of running ipShield on mobile platforms. So the plot that we have here is the time to load rules into memory and also for the rules to take effect. Now, if you consider applications on Android, they access sensor data in 4 different modes. So these mode corresponds to different rates at which they access sensor data. Now, in the sensor delay normal and the sensor delay UI mode, which are basically the preferred mode for efficiency of power, the intersample delay is large enough that even 200 rules can be brought into effect. For sensor delay game, we observed that for 50 rules, around 2 samples are being released without being subjected to the new rules. And for sensor delay fastest, which is the fastest mode of acquiring sensor data, which is very taxing on the battery, you'd release around 6 samples. And finally, we evaluated ipShield, the memory as well as the processing overhead of running ipShield on Android. And we observed that compared to AOSP, which is the base level, the Android open source, the basic open source from which we actually derived ipShield, our memory overhead is less than 1 MB. In fact, for suppression, we see that the memory overhead is reduced. And that's because we are not releasing data, so we really don't need to store that data. So the memory consumption actually reduces. So in conclusion, we designed and implemented ipShield. We propose the use of inferences as the currency for privacy and utility specification. So instead of sensors, users should have a higher level privacy abstraction. We advocate that the burden of rule configuration should not be on the user, but it should be shifted to the system. And we provide better insight into how data is being used by the system and also visibility into potential risk and consequences of sharing data. Going forward, we want to design a better rule recommender which will not only provide binary policies on sensors, but actually tell us how to obfuscate sensor data in a more principled way. We want to augment ipShield with static analysis of app code because it provides us better visibility into what an app is doing with the data. So instead of generating conservative rules, we can have more flexible rules. And finally, we want to allow crowdsourcing to actually bootstrap rules. ipShield is open source, and all the source code can be downloaded at this following URL. We also have a demo today at a poster session, so please feel free to visit our stall and check out the application. Thank you.
Jaehyun Jung, Microsoft Research. So how would you capture the correlation between different inferences? So I assume that, let's say that if I want to, the location is a whitelist, whereas activity is blacklist. By disclosing location, I may, that may disclose activity, right? So unless you capture this correlation, your optimizer might fail to find solutions.
So if you look at the rule recommender that we have in ipShield right now, in this, we do not model this correlation between the different inferences. We rely on the user to kind of select the inferences in a proper way. But having said that, we have tried to model this relationship between the different inferences. So one way in which we have tried to model this is using a dynamic Bayesian network. So we actually take all these different inferences and see how they are, what is the causal relationship between these two inferences. And we are in the process of integrating this model into ipShield. So this is something which we have looked at. But yes, if you look at the current model of ipShield, we really do not have that model in this particular paper.
Okay, thank you.
Saman Zunuj, University of Miami. So I really like the fact that you're defining policies to access sensor by applications, sensor data basically. But the privacy violation may also happen due to indirect data flow. For example, an application which has access to GPS could just save that GPS data in an SD card file, which is accessible by all the applications, and then later, second application later on could access GPS from the SD card, which you do not monitor, and some sensor that is allowed, and then kind of with correlating those information could cause privacy violation. I'm just wondering how you would or you could address these indirect data flow-based privacy violations.
Sure. So that's a very good question. So if you perform a static analysis of the app code, that's one of the ways in which we can understand how data is being used by the app. So right now in ipShield, what we do is we say that if an application is using GPS data and you really don't want a particular context to be revealed, in that case you have options such as suppressing the data at that point. But what we do not know is of these hidden or covert channels that could be used by an application. So we don't keep track of these channels. So what happens is that because we don't keep track of these channels, our policies could end up being conservative. But if we do static analysis, and that's what we are trying to achieve as part of the extension of this work, is we are trying to build this static analysis capability within ipShield, and that will allow us to have rules which are more flexible in nature and which will allow us to identify these different covert channels. So I think of this as covert channels, and right now we do not handle covert channels.
It's not directly like exactly covert channel, but it's kind of the indirect data flow.
Absolutely.
Right, yes, thank you.
Thank you so much.
Singapore from the University of Washington. So, for the context, you use kind of whitelist and blacklist, which means that you need to all predefine the set of those contexts. So, how could the system provide those kind of contexts for every application? Is it actually feasible to?
So that's what I mentioned in the Inference Database, and that's a very good question. That is, how do you know the entire universe of inferences that could be made? So, that's like a moving target. So we need to keep, so what we have done is we allow crowdsourcing of this thing. We allow users to go ahead and, add newer inferences. So that way we can make ipShield aware of the existence of those inferences. But so the other alternative is to have a very strong context engine. What we have started to have in ipShield, we have a very simple prototype of that. But even then, the problem is, it's like protecting against the unknown. So if we need to know that there exists an algorithm which could take these sensor combination and map it to an inference. If we really don't know about it, then we can't do much about it. So we need to know about these inference to protect it.
Right. Another thing is if you have that many contexts, sure. quick question. So that many contexts, how the user could understand those
We're
things?
trying to stay on time, okay?
Sorry, we can take that offline.
Sure.
Okay. Thank you very much. Let's take this speaker down.